Yep.
Did you delete 410?
Did I delete 410?
410 Discord?
Did I?
I'm not really anymore.
I deleted the one from last spring.
Yeah.
Yeah. I deleted one from last spring. Yeah.
All the memes I made of you.
You should have saved them. It's mostly just to save clutter because I have a lot going on in my Discord, so I delete the old ones.
Yeah.
Oops.
I lost my phone on Sunday, so I can't look up what my email was. So the username is just the start of your email, right?
Yes, yeah. It started email, and then I think it should be your usual password for your
Use your password. Can you look up what my email might be? I know I sent you an email. Well, I mean, I sent you the forwards here, but
Yeah.
name starts with Aaron. I thought it was just like first and last name. Oh, the other Aaron.
Oh, there.
Yeah. Yeah, I've been trying that.
What's everyone else? So everyone else, you're just using your Cal State Fullerton ID and then your password to get onto the computer. I wonder if it's yeah, you might be because you just started this semester, right?
No, I've even used this computer lab before, which is why it's like unusual. It's not working.
Yeah, I'm not sure. It's actually my first time in here too since last year.
I'll keep trying then.
Yeah. Sorry about that.
No worries.
Okay, so let's go ahead and get started today. All right, good evening, everyone. Welcome to EGME 540 again, but this time in person. So, really happy to see everyone here. So I am going to run a little bit late to this class because I do have one right before this. But was the door open when you guys got here, or did someone have to open it for you guys? It was open. Okay, good. I don't know if I'm the last one in here though, so I don't know if I'm gonna lock it, but I'll say after class to figure it out. But
You know if it's open like well before class or?
that I'm not sure. I can check tomorrow morning when I come in and to see if it's open here, and then I could send an email to you guys to let you know. But usually the other computer lab 304, that one's usually more open, or at least you can ask someone to open that one for you. Just say that you need to use ANSYS or something like that. Okay. Yeah. All right, so it's great to see everyone's faces. Okay. I can only see it blurrily though because I took off my glasses because it fogs up because of the mask. But I'm glad you guys are all here. Okay. I know that this semester is going to be really weird, and so you can see obviously right now I have Zoom open, and so I want to have flexibility for for the cases where maybe you guys get sick or you don't feel comfortable coming to class. You can still join the lectures virtually on Zoom. Okay, so I'll be here physically every single day, and so if you guys come here, you can of course see me. But if you can't come to campus for some reason, but you still want to participate in the lecture, the option is there for you on Zoom as well. Okay, and that's going to be available for the entire semester. Okay? And so I see that we do have 3 people on Zoom, and so hello everyone that's virtual, but we also have a lot of people here, which is great. Okay. Okay, so how's everyone doing today? Good. A lot of thumbs up. Good. Happy to be back. Yeah, I'm happy to be back too. I was telling my last class, last class was a little bit strange for me because it was kind of my first time standing in front of a classroom in a while, and so I kind of had a lot of jitters, and so I had to tell like a couple of jokes and stuff just to get going. But I feel much better now, now that I've kind of gone through that once. But it's also just a lot nicer too to have some interaction. And so I was telling my last class that whenever I tell a joke or something like that, it's so nice to hear people actually respond to it and laugh. Because for the last year and a half, I would say something, and the only person that would be laughing would be my fiance, and she's just laughing at me because I'm just telling a joke to just like my computer screen, and no one's laughing. So it's so good to have people laughing with me now instead of at me.
Well, I won't make a sound on purpose.
Okay, and so let's get into today's lecture. Okay, and so as you guys all know, this class is a finite element class, right? But actually, this class is a lot different from the ones I've taught in the past, because in the past I like to focus a lot on kind of the theory behind finite elements, just because I think it's something that's really important and cool. But for this class, this class is explicitly focused on just the practical applications of finite elements, and so we're going to spend basically the entire semester doing that. But I do want to spend one day talking about some of the theory behind FEA. Okay, so we're going to just be spending today doing that. Just because I think it gives you kind of a more holistic understanding, a whole more holistic appreciation for some of the methods you guys are using. Okay, because what I find is that I think learning to use the software is really nice and really cool, but I think if you don't really have an understanding of what's going on underneath the hood, it can be difficult sometimes to kind of troubleshoot when things get wrong, or to give kind of a whole a better explanation for what you're experiencing. And so that's kind of what the goal of today is. Okay. And so the goal today is just to kind of, explain, some of that theory behind it. But, today's the only day. Okay. And so after today, we're going to be focusing just on practical application. How do we use ANSYS effectively? Just because, I want you guys to come out of this class feeling confident that you can use ANSYS in a professional setting. Okay. All right. And so let's get started with today's lecture. Okay. And please let me know, people on Zoom and people in here too. Like I know I have my mask on. And so, it's, I don't know how the audio is going to turn out. And so if you ever have trouble hearing me or anything, just raise your hand, just let me know, shout in the Zoom call or whatever. And, I'll be happy to repeat whatever. Okay. Okay. So let's get started. And so today we're going to learn about the theory. Theory behind FEA. Okay. All right, so just like I mentioned before, for this class, we're going to be focusing pretty much exclusively on the practical application. I say almost exclusively, so every day except for today, okay? But we should learn a little bit of the theory behind FEA, just so that you kind of have an understanding of, when you hit solve in ANSYS, you kind of have an understanding of what's really going on underneath the hood, okay? All right, and the purpose of this is like I said, to have a deeper understanding of it, but I think it also gives you a better idea of what are the full capabilities of what FEA can actually do, okay? And so you'll see that, ANSYS is a really great software, has a lot of things that it can do, but even ANSYS is just kind of barely scratching the surface for what finite elements as a whole method is really capable of, okay? And so by the end of today's lecture, hopefully you guys get a better idea of, what FEA is as a method and what it can really be used for in general, okay? Okay. And so first thing I want to say is that at its core, as finite elements just by itself, it actually has nothing to do with computers at all, okay? Okay. And so actually, like if you look at kind of the history of the development of FEA, finite elements was actually developed kind of way before computers actually became really a thing, right? But it was one of those things that someone developed, and then people looked at the theory behind it. They looked at how it can be used, and they thought this is useless. This can't be used for anything, right? It wasn't until that computers started really getting powerful that people realized that hey, this finite element thing that wacko created, like dozens of years ago, we can actually use this to actually solve practical stuff. Okay. And so at its core, finite elements, what it really does is that it gives you a way to go from a differential equation, which is something that's really complicated and hard to solve, and turn it into a system of algebraic equations, okay? Oh, actually, before I continue too, so I did this morning. I took a look at everyone that's on the wait list, and I put in a request to the department to add everyone that's on the wait list. So I think there were 5 of you on the wait list, and so you should have gotten an email sometime today from Nathan from our department to officially add the class. And so, I decided to add everyone just so that we can all take the class. Okay. And so an example of this would be like taking the heat equation. Okay. And so the heat equation is this kind of nasty piece of equation here. Okay. And so this is the heat equation. It's not even in 3D, but you can see that we have a lot of really nasty terms. Okay. Okay. And so this heat equation here, this is basically an example of a differential equation. In this case, it's a partial differential equation. Okay. Okay. And as you can imagine, that's really nasty to solve, right? So if you've ever taken a PDE's class, or maybe seen this in a previous heat transfer class, this is to put it bluntly, like this is a bitch to solve. Okay, it's not fun. And so what finite elements does is that it takes a system like this and transforms it into a system of algebraic equations. Okay, and so kind of the most common the most common way that we express a system of algebraic equations is with a matrix. Okay. And so I think the most common notation for an algebraic equation would be AX is equal to B, where A is some large square matrix, X is your solution vector, and B is your forcing vector, right-hand side vector. Okay. And so this right here is algebraic system. Okay. And so, that's all that finite elements does. And so, finite elements has nothing to do with computers. It just transforms this differential equation into an algebraic one. Okay. And so it seems like it's, the person that invented finite elements is, came with the logic that, differential equations, they're really hard to solve. Okay. But if we can transform them into algebraic equations, then this is something that's much more tenable, much easier to solve. Okay. The problem with that is that, when you apply finite elements, this algebraic system is so large and so dense that it becomes impractical to solve by hand anyway. Okay. And so I'm talking systems that are probably like, 10,000 rows by 10,000 columns. Okay. Okay. And that's a really light problem. So 10,000 by 10,000. Okay. But you can imagine that, back in the time of, even before boomers, I guess, way before that, if someone tried to give you a 10,000 by 10,000 linear system, they told you to solve it by hand, you'd probably tell them to go fuck off or something like that, right? Like no one wants to do that. I complain when I have to do anything more than a 3 by 3. And so, 10,000 by 10,000, that's crazy. Okay. It wasn't until that, computers started to become a thing and computer algorithms started to become more powerful. They say that, computers are really, really good at solving algebraic equations, especially really big ones. Okay. And so it wasn't really until then that finite elements really started becoming a thing where, you can take this differential equation, which normally is impossible to solve on a computer. Okay. But if you can use some theory, you can use some techniques to turn that differential equation into a very large linear system, then you can pass that linear system onto a computer, and then they can find the solution for you. Okay. And so I think, a lot of times people associate finite elements with, it's this computer thing or it's a computer program. But at its core, it really has nothing to do with that. It really only started to become a computer thing once we got to this point with these really large linear systems and saying that computers are actually really good at solving those. Okay. Okay. So any questions on this so far? Okay. Okay. And so why is this relevant for engineering, right? And so we haven't really talked about engineering at all yet, right? So all we know is that finite elements can take a differential equation and then transform it into an algebraic one, okay? And so the reason this is useful for engineering is that it also just so happens that a lot of engineering systems of interest, they're also governed by differential equations. Okay. And so on the last page, I showed you the heat equation, right? And so obviously, heat equation is very important if you're doing any kind of thermal engineering. Okay. But for this class, we're going to be doing a lot of structural engineering. Okay. And so structures have their own differential equation that they follow. And I think one of the other big areas is fluid mechanics, right? And so probably everyone's heard of the Navier-Stokes equations. And so that's kind of one of the more famous ones. That's also a differential equation. Okay. And so if you want to do any kind of engineering analysis or engineering predictions, you're going to be running into a differential equation one way or the other, okay? And so that's how, and so once people started making this connection where it's like engineering system, differential equation, finite elements, algebra, computers, that's when kind of the whole thing kind of became full circle. And that's when things really started, that's when finite elements really started to become associated with being an engineering tool. It's kind of this whole connection. And so I drew this flow chart for you just so that you kind of see kind of the progression of logic. Okay. Okay. And so if you start with the physical engineering system, okay. And so this could be a structural system, it could be a thermal system, a fluid system. Okay. What you can do from there is you can extract the governing differential equations. Okay. So every engineering system is governed by differential equations of some kind. Okay. Okay. What you can do is you can use FEM. And so FEM stands for finite element method. So I use FEM, FEA. They mean the same thing. I'm just not disciplined between them. Okay. Right. And so by FEM, what you could do is you could take these differential equations and you create a system of algebraic equations. Okay. Okay. Right. At this point, now that you have a system of algebraic equations, your computer is like, hey, I'm really good at solving that. And so you use your computer. Okay. And you find a solution. Okay. And so after you get that, then that's your solution to your algebraic system. Okay. And then from here, you start to enter post-processing, right? Because right now, all you have is just the raw solution to that huge linear system, right? And so to actually transform that into a form that's actually useful for performing engineering analysis, you have to actually do a little bit more post-processing. Okay? And so thankfully, ANSYS does this for you. Okay? And so if you remember at the end of the activity last week, we saw kind of color contours for like deformation and stress. Okay? Once it gets to that point, the computer's kind of already done some of that post-processing for you. Okay? And so usually I like to call that the engineering results of interest. Okay. Right. And then what happens next is that you as an engineer, you take that information and then you use that to actually perform your engineering work. Okay. And so the last stage in this is, engineering, I call it engineering design and analysis. My stylus is kind of freaking out right now, but that's usually the cycle. Okay. And so when you boot up ANSYS and when you run a simulation, this is kind of the flow chart that you're following, whether you're conscious of it or not, because a lot of this is handled by ANSYS itself. Okay. And so in fact, if we draw this box around these 4 steps in particular, okay, these are the steps that ANSYS kind of handles for you, kind of without you kind of really knowing what's going on. Okay. And so you as an engineer, all you have to do is you have to define, what your physical system is, okay, what kind of physics that it follows. You input that all into ANSYS, and then at the end, you take the information from ANSYS in order to perform your engineering work. Okay. Okay. And so any questions on this so far? Okay. All right. And so what does this mean for what does this mean for the capabilities of FBA, right? And so what this means is that you can use finite elements on really any system that's governed by differential equation. Okay? And so you're really not just limited to like structural systems or dynamic systems or fluid systems or thermal, right? Because if you open up ANSYS, you see that huge list of things, right? But even then, you're not even just limited to that, right? And so finite elements can actually cover a lot more than that. But if you do want to do something a little bit more interesting, you probably have to write your own code for that. And so, we're not going to be covering that in this class, but I just want to make you guys aware of those kinds of capabilities. Okay? Because now with the advent of like the internet and open source programming, a lot of people are creating kind of their own kind of homebrew finite element codes to solve really niche problems. Okay. And the reason they can do that is because of how flexible finite elements is as a method. Okay? And so as long as it exists as a differential equation, you can use finite elements to solve it, kind of no matter what that differential equation is, in theory. Okay. And so, a lot of the niche projects you see out there kind of follow this exact same, methodology. Okay. And so that's, kind of an overview of what finite elements is capable of. Okay. So now let's talk a bit about, how do we actually set up a problem in order for finite elements to solve it? Okay? And to do that, we have to talk about something called boundary value problems. And so I'll abbreviate it as BVP just because boundary value problems a little bit long. Okay. And so boundary value problem, it's a you can think of it as a mathematical expression of the type of problems that you can solve with finite elements. Okay. Okay. And so intuitively, what you can think of when you think of a boundary value problem, you probably obviously think of like a physical problem with a physical boundary, a physical geometry, solving like real physics. But in reality, it doesn't have to be like that. And so, like if you spend any time around applied math people, they'll call certain things boundary value problems, but you'll look at it and you'll wonder, what the heck am I looking at? But for engineering, we mostly restrict ourselves to strictly physical stuff, but just know that this definition that I'm giving you is a little bit more general than that. Okay. Okay. And so, this is really useful for you guys to think about. And so, if this is one important point I want you guys to take away from that is that whenever you go to set up a finite element problem, it's always really useful to think about, what's the corresponding boundary value problem that I want to solve. Okay. Okay. Because when you think of things in terms of boundary value problems, you think about certain characteristics of your engineering problem that you might not have paid attention to before, but those characteristics are really important when you're defining finite elements. Okay, and so in particular, there's three components of a boundary value problem that I want you guys to think about. Okay. And so first is your domain. Okay. And so your domain is simply the geometry and the boundaries on which you want to perform your analysis. Okay. And so for our activity last week, we did our plate with the hole. Our domain would be, physically that plate with the hole in the middle. Okay. And so for most engineering applications of FEA, this is going to come from your CAD model. Okay. So you have a CAD geometry that's going to define your domain. Okay. But it could really just be, all it really just has to be is just kind of a physical boundary on which you want to perform your analysis. Okay. Okay. And so, you maybe not so much in this class, but I like to use this in a lot of my classes where, we can call our domain this arbitrary potato. Okay. And so it's really just an amorphous blob that I can't draw any better, but it looks like a potato, so we call it that. Okay. And then to specify kind of the interior of this geometry, I like to use the symbol omega. Okay. And so the omega kind of looks like, kind of like that. Okay. And so whenever you see, a domain omega, what that means is this, the interior. Okay? And so all of like the white fleshy parts of the potato, that's given by omega. Okay? And so the other part of your domain is the outside. Okay? And so if you think about kind of the brown skin of your potato, we call that the boundary. Okay. And then my symbol for the boundary is I give it a this partial sign and an omega. Okay. And so that's the distinction I make between them. Okay. So the reason we have kind of the symbol for the boundary is that we have the omega there just to kind of correlate it together with the interior. Okay. But then we add that kind of partial sign in front to denote that this is the boundary. This is the exterior of our domain. Okay. All right. And so, the domain, is oftentimes fairly obvious, and a lot of times it's kind of already set for you when you do finite elements. Okay. And so when you're doing finite elements, a lot of times you're working with a certain CAD file. or you have your geometry that's kind of already obvious. Okay? But a useful question to ask yourself whenever you're setting your geometry is, what is a good domain, for the analysis that I want to do? Okay. And what I mean by that is, sometimes you might not have to use the whole CAD file. Right? And so, if you're running a simulation on a very complicated geometry, but you're really only interested in the stresses at in a certain component or a small part, maybe it's more useful just to do the analysis on that small part and not do the analysis on the entire thing. Okay. I remember, one time in the past, a student was doing a finite element project, and he was doing a finite element project on a bench press. Okay. And he was interested in seeing, how much weight can you put on the bench press before it's in danger of breaking. And so what he found was he found a CAD file of the entire setup, right? So he had the bench, he had the weight rack, he had the weights, he had all the weights on the bars, right? But in reality, what he's really interested in is he just wants to do a simulation on the bar. And so doing the bench and everything, it was kind of pointless because none of that stuff you're worried about breaking. The only thing you're worried about is just the bar itself. Okay. And so when you're defining your domain, especially if you're doing kind of a project on your own, it's good to think about what am I actually interested in, and can I center the domain on just that without any of the extra stuff. Okay? And so what he ended up with was that he ended up with the situation where his entire geometry was stress-free. So he's like, wow, great, everything has zero stress. But in reality, if you look at one part on the bar, that's like, it's saying, help, please help, I'm about to break. And so, but it's really hard to see because you have this entire domain, okay? And so when you're selecting your domain for your finite element problem, really give it some thought and saying, what do I really need to actually perform this analysis for, okay? Okay, so any questions on this? Okay. All right, and so that's one part of a boundary value problem. Okay. The next part is the governing equations. Okay. Right. And so after the domain is established, you have to determine what kind of physics or what kind of behavior am I going to expect from this domain. Okay. Okay. Right. And so you have to ask yourself, what kind of physics am I expecting for this domain? Okay. And so as an example, let's think of our activity last week. Okay. And so if you remember from our activity last week, one of the first things that we set was that we want to solve a static structural simulation. Okay. Okay. And so what that does is that it tells ANSYS that these are the equations that I want to solve, right? And so you tell ANSYS prep all the structural equations because that's what we're interested in. Okay. And so that's kind of the most straightforward case is if you have just a single physics, right? And if you're solving just a structural problem, it's normally just fine. Okay. But you can also have situations where you have multi-physics. Okay. Right. And so multi-physics, it could be an example where you want to solve kind of multiple kinds of equations or multiple systems at the same time. Okay. And you can do that, okay? And so if you have like both thermal and fluid stuff going on, or thermal and structural, or maybe fluids and structural stuff going on, you can solve multiple physics at the same time. Okay? And so one example that I like to that a student group actually did this in the past was that he was doing a finite element analysis on a brake pad. Okay, and so he had a situation where he had a brake pad that was being engaged and stopping a vehicle from going. Okay, and so he wanted to look at what's the if the brake pad was structurally strong enough to do this. Okay, but as the brake pad was slowing down the wheel, you had a ton of heat coming in through friction. Okay, and so what he had to do was he had to solve both a thermal equation to solve for the temperature distribution in the brake pad, as well as a structural simulation to see how much it can withstand. Okay, and it becomes even more complicated from the perspective of a lot of times your material properties of things like your Young's modulus and your density, they depend strongly on temperature. Okay, and so you need, in order to get an accurate simulation, you actually need to solve both equations at the same time. And so as the temperature changes, you can tell ANSYS to change the Young's modulus or change the density, and that's going to affect the results of your structural simulation too. Okay, and so I don't have anything really explicitly planned for multiphysics because it is a little bit expensive to run, but but if there's strong interest, I can whip up something near the end of the semester, or just kind of be aware that it's out there. It's not the easiest to do, and so there's a lot of challenges to multiphysics in terms of how you set up the mesh and how you set up the the simulation parameters, but it is possible in a lot of really interesting situations. It does do multiphysics. Okay. And another thing to consider when you're setting your governing equations is that there's some variations within a group. Okay. And so I think the best example of this that we'll go over in this class is that there's not just one structural equation. Okay, and so there's static structural, which is the one that we've done before, right? But you also have to consider is there going to be any plastic deformation? Okay. Okay. Is there going to be any nonlinear deformation? Is there going to be any buckling? Okay, so that's another consideration. Right. And so there's not just one kind of equation that governs the whole thing. And so there's lots of different variations to the equation that you kind of have to be aware of. Okay. And we'll go over a lot of these for structural. Okay. And so we'll go over when do you want to use plasticity, when do you want to use nonlinearity, when do you consider buckling? Okay. And so when you're setting your equations for your finite element analysis, you really want to say, or you really want to ask yourself, what kind of physics am I expecting, and am I loading in all the appropriate features in order to account for that behavior? Okay. Because if you do have a situation where you do have kind of plastic deformation, but then you don't kind of explicitly tell ANSYS to look out for that, you might get a solution that ends up being completely wrong. Actually, someone was doing kind of the previous activity, and he kind of pointed this. He kind of saw something like this happen, where I think one of the variations that I told you to do on the last activity was to increase the load really significantly. I think up to 25,000 megapascal. Okay? And what he experienced was that when he did that, ANSYS gave you a warning that said, I'm experiencing very large deformations. Do you want to turn on non-linearities? Do you want to turn on plasticity? Okay. And what he found was that when he did turn those things on, he actually got a result that was very different from when he just did static structural. Okay, and so these are kind of really important things to know. And in this semester, we'll be going over a lot of the subtleties of when you would use one thing or the other one. Okay, so any questions on governing equations? Okay. All right, so that's part 2 of the boundary value problem. And so the last one that I want to go over is the boundary conditions. Right. And so the boundary conditions, just like its name kind of implies, what it does is that it defines how the solution will behave at the boundaries of your domain. Okay. Okay. And so in other words, what the boundary conditions will encapsulate is how does the outside world, how does everything outside geometry, how is that going to be interacting with your physical system? Okay. All right. And so most commonly, you won't hear the term boundary condition all that often in ANSYS, but the way that we usually define these in ANSYS are things like loads and things like constraints, okay, or supports. At least in a structural context, that's what we describe them as. Okay. And so if we go back to our example from the plate, right? We actually applied two boundary conditions on that. And so the first boundary condition was the fixed support, right? Remember that we took our plate and we fixed it on the left-hand side, okay? And so that tells you that there's something outside of our plate that's fixing that part, so it's causing it to not move. Okay? And then the other boundary condition that we had was the pressure on the right-hand side, right? So we had that pressure that was kind of pulling the plate to the right. Okay? And so that's simulating, maybe like the Hulk is taking it and pulling the plate that way. Okay? Again, it's some kind of external factor that's exerting influence on how our physical system behaves. Okay? And so the way that you express those external factors is always going to be through your boundary conditions. Okay, and so boundary conditions, they can be a little bit tricky to set up. And so a lot of times if you have kind of a practical situation, it might be difficult to look at it and say, what my boundary conditions are. Okay. Okay. Right. And so a lot of times what you might have to do is you might have to make some approximations about how particular loading interacts with your model. Okay. Because it might not be possible to to include kind of a detailed description of that loading. Okay. And so one example that I can give you is that we'll do later this semester actually is, say you're doing a finite element analysis on a bridge. Okay. And so a bridge is subjected to, obviously the loading from all the cars that drive over it. Okay. And so to come up with a boundary condition that simulates, maybe, a few dozen cars driving over the bridge, maybe at different speeds, right? And so let's say that there's traffic, maybe there's no traffic, maybe there's, some cars are going faster than the other one. Okay? That's a really hard thing to determine. If you can convert all those cars moving over the bridge into like a single force or a single pressure, that's really difficult to do. And so, if you're doing a finite element analysis on that, you might do something like, you might take like the weight of all the cars and just apply that as a flat pressure. Okay. And that's just a modeling assumption that you have to make just to make things easier for yourself. Okay. Another way to think of boundary conditions as, these, you can kind of think of them as kind of like the instigators or kind of the inputs to your model, okay? Because without boundary conditions, a lot of physical systems would just be really boring, right? And so if you look at our plate, right? And so if we look at the activity that we did last time, right? If we didn't have any force on it, that plate would just be chilling, right? It would just be sitting there minding its own business. It's not going to deform. It's not going to form any stress, right? It wasn't until that we applied that loading. It wasn't until that we applied that pressure. That's when something interesting started to happen. Okay. And so a lot of times, if you read kind of the literature on finite elements, or you read some textbooks, you might see boundary conditions described as like the inputs to your model. Okay. Okay. And so without boundary conditions, you oftentimes you won't get anything interesting at all. Okay. And so, I think when you're first being exposed to this stuff, at least, I placed a lot more kind of importance on the governing equations, right? And so the governing equations, that determines the physics, right? And so I think, that's the most important thing. But actually, without boundary conditions, your governing equations don't do anything just interesting. Okay. And so if you don't have any boundary conditions, your governing equations, the answer for that is probably just going to be 0. Okay? It's not until you add boundary conditions that things actually start to get interesting solutions. Okay? And so I know it's the third thing that we're going over, but I would actually say boundary conditions are probably the most important one out of the ones that we talked about. It's also the hardest one to do really well. Okay. And determining those boundary conditions might be, really hard. And a lot of times it drives a lot of other decisions that you make about like the domain and the governing equations. Okay, because a lot of times when you're doing a finite element analysis, a lot of times you set your geometry or set your equation based on where it's going to be simplest to apply the boundary conditions. Okay. And so if we take the example I was talking about earlier with the bench press, right? And so we talked about before that you don't have to model the entire bench press in order to just get the result of just a small part, okay? But you also have to be careful too that you make the domain big enough such that the boundary conditions actually make sense. So actually, I'll draw it out on the next page. But before I do that, are there any questions on this? Okay. All right, and so let's take a bench press. Okay. Okay. And let's take a situation where the bars are kind of resting on the what do you call it? The rests. Okay. So you have a bar, or at least a simplified version of the bar. Okay. And let's say that it's being held at these two locations right here. Okay. There's one stop and there's another stop. Okay. I know a bench press doesn't look like that, but I'm a terrible artist, and so just bear with me, okay? And so, if you put weights on this thing, okay? Okay. What I would generally expect from this, and the student found this too, was that most of the stress is going to be concentrated at the supports, okay? Okay. And so whether or not the bar is going to snap or whether it's going to stay intact, that's the area that you want to look at, because that's where stress is going to be the highest. And so if you looked at this and you looked at where we circled these results, it's really tempting to say that if that's the only location that we're interested in, why don't we just make a finite element simulation on just that segment? Okay. And so what if we just do a small segment of the bar like that? Okay. And it's being supported like this. Okay. why don't we just do a finite element simulation on this small guy, okay? Because that's going to save us a lot of time and effort, right? And so instead of simulating this entire bar, we're only just simulating just a small segment, and that should be really cheap, okay? Okay. The problem with this is that, if you are doing just this small segment, the question is, how do you apply the load on this small segment, right? How do you apply the boundary condition? Okay, because if you look at our original figure here, our loads are being applied, on the very tips of the bars, right? And so if we don't include that area, if we don't include that region inside our domain, it's going to be really hard. It's not impossible. I'm not saying it's you can't do it, but determining, what kinds of loads that we put on this surface and on this surface, okay? Or in other words, how do we transmit the weights from the weights on the outside? How do we transmit that to those small blue segments? That's not trivial. That's not an easy thing, okay? And if you want to get an accurate simulation on just this small segment, you need to make sure that those weights get transmitted accurately to those small segments, okay? And so that's really hard to do. And so a lot of times it's just simply easier to say, let's just simulate the whole bar, because then we can just, we can put the weights where they're supposed to be, and then our boundary conditions make sense to us, okay? Okay, all right. And so that's boundary conditions. And so, and so those are the three aspects of a boundary value problem I want you guys to think about. So I want you guys to think about domain, okay? And so what kind of geometry are you doing a simulation on, and what's kind of the most optimal domain that you can set, okay? 2 is the governing equations. And so, what kind of physics are you expecting in this domain? Do you need to consider multiphysics, and what other types of like plasticity and nonlinearity do you need to consider? Okay? And then 3rd is the boundary conditions, right? And boundary conditions, remember, is how external forces are, influencing your domain, okay? And you need to think about all these 3 things whenever you want to finite element simulation, okay? Because they all come in one place or another. Any questions on any of this before we move on? Okay. All right, and so now that we've talked about boundary value problems, let's talk about the types of equations that you can run, or some of the more common types that you can run in finite elements, at least in ANSYS. Okay. Right. So remember, FEM, you can solve any differential equation out there. Okay. But obviously the ones that actually model physical behavior, those are the ones we're going to be solving most often. Okay. And so I'm going to give you here a short list of some of the more common ones that we'll solve in ANSYS. But even this is not a comprehensive list. Okay. All right. And so the first one that we'll look at, and this is the most common one that we'll see in this class, is linear elasticity. And so linear elasticity, what these equations tell you is they tell you how a solid object will deform and become stressed as a result of external loading. Okay. And so the mathematical form of these equations is, it's kind of a spin off Newton's second law, actually. Okay. And so you don't have to know this because we're not actually going to be solving this. ANSYS is going to be solving this. But in case you're curious about what the equations look like, basically you have the divergence of the Cauchy stress, okay, plus any kind of external force. Okay? This is equal to the density times the acceleration. Okay, so this is Cauchy stress. Okay. Okay. Or I should say this is a body force, not an external force. Okay, but it doesn't really matter. And this is acceleration. And this is density. And so if none of these symbols and none of these words mean anything to you, it's okay. You know, this is just kind of for curiosity's sake. But you know, this is basically the equation that ANSYS is solving underneath the hood. Okay. All right. And so why is it called linear elasticity? Okay. And so that's actually kind of the key. That's kind of the key point to this. Okay. And so the reason it's called linear elasticity is that the relationship between stress and strain within your solid is linear. Okay. And so you probably are familiar with this equation right here. We have sigma, or the stress, is equal to E times epsilon. And so you just have a simple linear relationship in between the two. Okay, where the key parameter here is capital E, where this capital E here is your Young's modulus. Okay. Or sometimes called elastic modulus, if you call it that. Okay. All right. And so, you know, whenever you hear the term linear elasticity, you know, what it really means is that there's basically a one-to-one relationship between stress and strain. Okay. I think another name for this equation is Hooke's law. Okay. You know, but there's a lot. So this works really well for a lot of solids, given that the deformation is small. Okay. And so if you have a structural situation where the deformations are small, then linear elasticity is a good option. Okay. Because once you start getting into regimes of higher and higher deformation, that's when things like plasticity, that's when things like nonlinearity start to come into effect. Okay. Okay, so any questions on this so far? Okay. All right, so let me draw you kind of a typical stress strain curve so that you kind of see where we are. Okay. And so typical stress strain curve looks like this. Okay. And so when you talk about linear elasticity, you know, you're mostly concerned with this region of the stress strain curve. Okay. And so as long as the strains are small enough, okay, so as long as you have small strains, you have this kind of linear relationship in between the two. Okay. And the nice thing about linear elasticity is that as long as you're within this regime, you know, if you remove the loading, if you remove the force, you know, your object is going to return back to the way it was before. Okay. But probably, as you guys know, that once you reach a certain point, so like once the deformation gets over a certain threshold, you know, this linear relationship no longer holds, and so you start to get this kind of you know, kind of this plateauing effect right here. Okay. And this region right here is plastic deformation. And so as you can see, you know, once you get to plastic deformation, then the relationship changes pretty significantly between stress and strain. Okay. And so if your finite element simulation is going to be within that plastic region, you know, you need to make sure you basically turn it on. And you basically tell ANSYS to look out for it. Okay. Because otherwise, what ANSYS is going to do is that it's going to assume that this linear relationship kind of holds on for eternity. Okay. And so it's basically going to assume that it kind of continues on just like this. Okay. All right. And that you basically are following this region up here. Okay. which would be totally wrong, right? And so you would get situations where the stress would become really high and the strain wouldn't be as high because you're continuing on with that linear curve. Okay. And so if you have a situation where the deformations are getting pretty large, you want to make sure that you're looking out for plastic deformation and see if that makes a big impact. Okay. And so when you're solving structural simulations, the primary variable that you're solving for is displacement. And so you'll hear me use the term primary variable of one. Okay. And so all that really means is that that's kind of the first thing that the finite elements is going to solve. Okay? And so when you're solving structural simulations, the first thing that it solves for is the displacement or the deformation. All right, and so that's elasticity in general. Okay, so that's static. That covers our static structural. Okay, so the next one I want to go over is heat transfer. Right, and so what heat transfer solves for is it basically determines how heat or how energy propagates through a solid. Okay. Right, and so the heat equation is often given by this. Okay. Again, this is just the equation, and so we're not actually going to be solving this, but in case you're curious. Okay. And so this is the equation that we solve for. Where this quantity right here, K, this is your thermal conductivity. Okay. And this Q term right here is thermal generation. And then this T here is our primary variable, okay? And so T here stands for temperature. Okay. And so when ANSYS or when finite elements first solves the heat equation, the first thing that you compute is the temperature distribution. Okay. Okay. So any questions on this? Okay. All right. So I would say that when you're first learning finite elements, those are kind of the two equations that you mostly stick with. Actually, heat equation is actually a lot easier to solve than the structural one. So if we're coming at this from a theoretical point of view, we'd probably focus mostly on thermal, but I think physically and intuitively it's easier to use ANSYS with structural, because I think it's a little bit easier to kind of see what's going on. Okay. But the third one I want to share with you, and actually this is the one that I actually use a lot more for my research, is for fluid flow. Okay. And so probably some of you might be familiar with the term computational fluid dynamics, or CFD. Okay. And so when you run CFD, you're basically using a method like this, where you're using some kind of computational technique, either finite elements or finite volumes, and you're using that to solve the Navier-Stokes equations. Okay. And so basically what you're solving for here is you want to determine how fluid will flow inside a domain. Okay. Okay. And this is in response to being exposed to some kind of pressure gradient or maybe gravity. Okay. Right, and so the governing equations for this is Navier-Stokes. Okay, so I'm actually a lot more familiar with this one than the structural equations. Okay, so the structural one I actually had to look up on Wikipedia, but this one I kind of know just by heart. So Navier-Stokes is partial u partial t plus u partial x plus v partial u partial y, as we only did 2D. And again, you don't have to write this down. I'm just kind of flexing for a second that I can write down Navier-Stokes, but you can see here that this is a differential equation, a very complicated one that you can solve with finite elements. Okay. Right. And so, because we have this really complicated equation, finite elements is extremely useful here, because otherwise, this is kind of a mess to solve. Okay. All right. And so just a note, if you want to use ANSYS to solve for fluid flow simulations, it actually uses a completely different program for that, and that program is called Fluent. Okay. And so, I'll admit that I haven't used Fluent all that much, and so I'm not all that familiar with it. I know the basics, and so if you're interested in learning, we can talk about that. But I definitely wouldn't class myself as an expert in Fluent. I've mostly used others, my own software for running CFD before. All right, and so when you solve fluid flow equations, the primary solution variable is the velocity. Okay. And so first thing that you solve for from Navier-Stokes is how the velocity is distributed. Okay. Okay. And so that's a summary of all the equations that you can solve for. Okay. And so, last thing I want to cover, and we might be able to finish up today. Okay. Is what is ANSYS actually doing? When I say that, we've already talked about how finite elements is taking these differential equations and putting them into an algebraic system, right? And so how is it actually doing that? Okay. And so I like to call this, peeking underneath the hood. So it's like you're kind of looking underneath the hood for how the car works. Okay. But in a very similar way that, if you simply open up your car and stare at your engine, you're not going to suddenly become an automotive engineer expert. Okay. And so, we're going to take a very, very brief look, but just know that, this section here, I've expanded this to an entire class. Okay? So you're just getting a very, very brief flavor, like just a brief whiff, but, I just want you guys just to kind of have some idea of what's going on underneath the hood. Okay. Okay. And really the driving force behind this is something called an element stiffness matrix. Okay. All right. And so, we've already talked about at the beginning that, what ANSYS is doing, or what any finite elements is doing, is that it's taking your differential equation and it's what I like to call assembling this gigantic linear system. Okay. And so I'll use the notation here, AX equals B, where A is this gigantic, this gigantic matrix, right? And so it might be, 10,000 by 10,000. It can be, 100,000 by 100,000. I've seen cases where it gets up to the billions, right? So it could be like 1 billion by 1 billion. Okay. And I'm not even exaggerating, that can happen. Okay. And so, what I want to go over is, how does it actually go about assembling this system, right? Because if you're talking about a system that's even 10,000 by 10,000, right? You're talking about 10,000 squared. That's the amount of matrix entries that you're determining. My brain's farting out, so I can't. 10,000 squared. You get it. You guys know what that is, right? And so the question is, how does it actually do that? And one thing we haven't actually talked about yet is the mesh, right? So if you remember, one thing we did in the activity last week was we took our geometry and we broke it up into, a bunch of simpler geometries, right? When we meshed our plate, we had all those really tiny squares. And so how does that actually factor into this method too? Because, we haven't really talked about it. Okay? And so that's kind of what I want to talk about here. Okay. So we want to say, how is big linear system formed? Okay. I shouldn't use big. I should use the real term for it. So it's the global system. Okay, global linear system. Okay. And so the way that it's formed, it's actually formed element by element. Okay. And so each of those elements that we had in our mesh, what ANSYS is going to do is it's going to visit every single one of those elements. And then what it's going to do is it's going to come up with what's called an element stiffness matrix. Okay. Okay. All right. And so what ANSYS will do it will visit each element. Okay. And then when it visits each element, it's going to determine kind of a much smaller linear system. Okay. Okay. And each of these smaller linear systems, these are called element stiffness matrices. Okay. All right. And so, I think it's probably easiest just to kind of illustrate what this means. Okay. And so let me draw kind of the global linear system over here. Okay. And so let's say that we have a global linear system, AX is equal to B. Okay. And, let's say that, for this situation, A is, 10,000 by 10,000. Okay? And so it has a lot of entries. Okay? And so the way it determines those entries is that, if you take, each individual element, okay, okay, each individual element has its own linear system that determines its own behavior. Okay. And so let's say that, okay. So let's say that this is 10,000 by 10,000. Okay. But for each individual element, we might have a much smaller matrix. Okay. And so this matrix might only be like 4 by 4. Okay. And so something that's reasonable. Right. And so the way that those kind of smaller systems are determined is they're determined by a combination of the element shape. Okay. And so depending on if you have a triangle, if you have a quadrilateral, okay. It depends on the size of the element, right? So it depends on how big it is, how curved it is. Okay? You combine that together with the governing equations, okay? And so depending on whether you're solving a structural equation or a thermal one, okay? All of those kind of come into play and they form this element stiffness matrix, okay? Which is much smaller. And then what you do from here is that, once you've determined this element stiffness matrix, you can insert that into the global one, okay? And so what happens underneath the hood is that this goes in here, okay? and then it finds kind of its place where it belongs. Okay, and so it's almost kind of like a giant jigsaw puzzle, and so you try to find where this element kind of fits into the global one. Okay. Okay. And then you insert that system kind of where it, where it belongs. Okay. And so here you have kind of a 4x4 system, right? And so what it needs to do is it needs to find kind of the 4x4 block within the global linear system, and then it's going to fit this element stiffness matrix into that location. Okay. And then if you do this for every single element that you have in your mesh, and so let's say that you have another element like this, okay, maybe another element that's over here, okay, another element that's over here, okay, maybe another element that's like over here, okay. You eventually do this for however many elements that you have in your mesh, whether it be 1,000, 5,000, or whatever, okay. Eventually, you're going to fill up this matrix with all of the entries that it needs to do, okay. And it's only at that point, once you've filled in, you've added all the contributions from the elements, that you can solve the system for, for X. Okay. Okay. All right. And then once you've reached that point, then kind of what happens is that your boundary conditions are then taken into account. And so once you form the giant linear system, then what ANSYS is going to do is it's going to take your boundary conditions, it's going to modify this global linear system according to the boundary conditions, and then from there you get your solution. Okay. And so that was kind of an ultra SparkNotes edition. So in like 10 minutes, we covered what an entire course would be dedicated to. But I want you guys to kind of have a general understanding of this, that each element that you have in your mesh, it's going to be contributing to the solution kind of on its own. Okay. And the way that it contributes to it is it kind of fits itself into this global linear system through its element stiffness matrices. Okay. Okay, so any final questions on this before we wrap up for today? Okay, all right, so that's all I had planned, and so that's it for theory, and so we have no more theory in this class, so you guys can all cheer. And so after this, we're going to be, I think on Wednesday we're going to be doing a little bit more review on structural mechanics, just because I think it'll make the future activities a little bit easier if we kind of are on the same page in terms of like stress and strain and what all those things mean. Okay. And so we'll do that for a little bit, and then we'll continue working on ANSYS. Okay? So thank you guys for coming today, and I'll see you guys on Wednesday. Yeah.
What's the symbol?
This is a different symbol too. So this is a partial.
Oh, this is a partial.
Yeah. And so I use both of the omegas here just to make they're from the same thing. But I use this. It's like a tube. So it's kind of like.
Yeah, I know. That's why I'm.
Yeah.
And we should pronounce it Dawa.
Oh, Dawa. I see.
In the Pakistani country, Dawa.
I see. Yeah.
Thank you.
That's all.
I'm not sorry, by the way.
All right. You too.
Do you mind taking a look at my model? I've been getting like this weird error when I was doing it at home.
Oh, sure.
I just recreated it over there. So when you get a second, I'll just.
Yeah. Let me talk to people coming out, and then I'll meet you.
Thank you.
Yeah.
You think it's possible to do this course in like half Zoom, half in person?
Yeah. So I mean, I have that, and so if you want to, actually for this class, we don't even have any projects. So actually, we don't have any exams. And so if you just want to be virtual kind of the whole time, and you're okay with that, then you can just be virtual.
Well, I have classes, two classes on person on Wednesday, so I probably will be here Wednesday, but this is my only class on Monday and I rush from work. So if it's possible to do it, like.
Yeah, no, it's totally fine. The only thing is,
With student version.
yeah, with the student version.
Oh,
it's-
I'm the one that couldn't change it from 2D to 3D.
Ah,
And I
okay.
went out of town this weekend, so I didn't get a chance to try to see what the issue is. But yeah, I still can't. Even when I restarted the program,
Yeah, we have.
I'll
That's
look
that's
into
weird.
it.
Yeah, try here when you get.
I already saw,
Oh, you did it?
yeah.
Okay, great.
And then, I mean, well, I did it on this computer, but I didn't bring my laptop.
Okay,
Well, if anything, I'll just uninstall it and try installing it again and seeing if that solves the issue.
okay. Yeah, the only thing is, when we're doing the activities, it's a little bit harder for me to help people over Zoom. And so here it's a lot of, I can just walk around and kind of point at your screen. And so, but if you
If I feel comfortable, then I'll probably do that, and if not, then I'll just start. Sounds
yeah,
good, thank
sounds
you.
good. Yep.
Hello,
Hi.
Raphael.
Nice to meet you.
So, our majority of our classes from here on out, with computers or
So it'll be,
more discussion?
so if you look at the schedule, the days where we have ANSYS activity, that's the only days we're gonna be working on the computer.
Okay.
Every day else is gonna be kind of like this, where I have a set of lecture notes and we kind of do kind of a lecture.
Okay.
But every other day, every day we do ANSYS activities, those are gonna be the lectures.
Okay. That's good. Thank you. Hey, Professor, how do I look at the number of elements in my mesh?
Oh, it's a good question. So if you highlight mesh inside, in the bottom left, there's a tag called statistics. And so if you click on the plus arrow next to that, that'll show you how many elements.
I basically clicked everyone except that. I was
Oh.
like, looking through everything and I was like, "Oh, I'm just gonna ask him. So I should have clicked it. Okay, so,
Yeah.
and then also I was wondering, so I haven't done that part yet. I was
Mhm.
trying to do it today, but I got lost. Like I came 2 hours early and I got lost
Mhm.
trying to find the E parking lot.
Ah,
And then like I basically got off the 57 and went around the whole campus
oh, shit.
because I was trying to look on the street and see lot E, but no, it's like right there next to the Marriott. Anyway.
It's so confusing.
So I ended up running out of time
Uh-huh.
and I just got to the 2.5 millimeter mesh, which is the first one.
Okay,
So the way you worded the question, I'm assuming that it's not just gonna be double the number of elements.
Right.
So, why is it because of the relationship between the surface area and like the area of the actual polygon itself?
Yeah.
Or
that's basically it. And so, when you set the element size, if I draw just kind of a simple kind of square right here, what you're setting is actually this length right here, right? And so this is kind of the edge length that you're setting.
okay,
And so if you make this half, right, and so you make both this length half and this length half, you're actually making the area 4 times smaller because
because it's a
area.
squared value.
Exactly, right.
Oh, because it's a polygon, so it's a square.
Exactly.
Basically.
And so the relationship you have in 2D is like kind of a squared relationship, which, so if you double the number of, if you make the edge size half, you end up with 4 times the amount of elements.
Okay.
But in 3D, what you'll see
Is it a triple?
yes, it's a cubic. And so if you have the edge size in 3D, it becomes
So
8 times. Yeah.
Okay, so then you have, what is it? So you have 27?
27,
27 times, isn't it?
8 times.
Wait, 8 times.
So it's 2.
Oh, it's 2
cubed.
squared,
Yeah,
or 2 cubed.
Yeah, yeah.
Okay, I was thinking of 3 cubed. for some
Mhm.
reason. Wait, so wouldn't you have 3? It wouldn't be 2? It would be 3? It wouldn't
so
be 3, it
the-
would be 2?
Yeah, the dimension determines the exponent, but if you make the elements 3 times smaller, then you end up with 27 times more.
Oh,
It
okay.
depends on how you reduce the size. But if we're talking just halves,
Oh, I get what you're saying.
then it
Okay.
would be 2.
So if you had so if we just did the same thing where you had a 5 millimeter mesh and then you made it 2.5,
Mhm.
but if you made it 3 times as small, then it would be 3 squared. Okay.
Exactly.
That makes sense. Okay, thanks, Professor.
Yep.
And then,
Were you able to log into the computer using your username?
Oh,
or-
yeah.
Okay,
It was
great.
just basically like, mine is J Delage, so I just did that and then put my password for my Cal State Force account, basically. That's all I
Excellent.
did. Yeah,
Nice, nice.
and then I'll see you in office hours tomorrow.
Okay.
I'm gonna try to
Okay.
get most of the assignment done, and then if I have any problems, I'll just, screen share tomorrow. And I think that'll be easier, so we have the program there.
Okay. Yeah.
All righty,
All
Professor.
right. Yep. See you tomorrow then.
Yeah, thank you. See you tomorrow.
Oh, let me answer Manuel first, and then I'll come to you. Yeah. So Manuel, I think there's the I actually forgot the author, but it's the one with the Asian name. Let me see. It's oh, it's only one, and so it's just Lee finite element simulations and ANSYS workbench. Yeah, yeah. So I'm following that one pretty closely for this class. Mhm. Yeah. So it's called it's on the syllabus, and so it's this one right here. So finite element simulations with ANSYS workbench 2020. I think they have a new version this year for 2021. I think they put out one every year, but it's all basically the same. It's just the positions of the buttons kind of changed slightly. But this is the one I've been using because I got it for free. Yeah. Oh yeah, okay, yeah. You don't have access to the canvas, but yeah, once you get access, then it should be there on the syllabus. Yep. All right, I'm gonna close this call because it's been recording for a while.